So I'm now going to do a problem from the problem sheet, which includes, it's a very long problem because it has all of the concepts of this chapter all together into one problem. So let's have a look at it. So consider the following three complex vectors. Okay, so this is now new for you. Now our vectors have i's around, the square root of -1. Yeah, so they are complex vectors. This means that for every time we need to do the inner product, we will need to do the Hermitian inner product. Yeah, so don't worry, we will see how this works. So as you can see, we have 5 questions, and they cover, so the first question covers if they are linearly independent, which you already saw. The second question talks about expanding a vector into these bases, v1, v2, v3. The third one is about projecting a vector into a direction. And then the fourth is talking about orthogonal basis or orthonormal basis. We have to check if this basis is orthogonal or orthonormal. And finally, if the basis is orthogonal, we can expand the vector into the orthogonal basis using a simplified recipe. So basically, we are going to repeat the calculation from B, but using a simplified recipe. So let's get on with it. So first, A. Are these vectors linearly independent? So remember, how did we check that? We had to check whether the system A1 times V1 plus A2 times V2 plus A3 times B3 equals 0 only has the trivial solution in which A1, A2, and A3 are 0. If there is any other solution, then they are linearly dependent. If the only solution is that the 3 A's are 0, then they are linearly independent. So this is a system of equations which we can just substitute the 3 vectors, and we get A1 times the first vector plus A2 times the second vector plus A3 times the third vector equals 0, 0, 0. So these are basically 3 equations, which is, and let's number them. Okay, so we need to solve this simultaneous system of equations. So first of all, from 3, we directly know that A3 equals 0. Yeah. Now we do from 2. So if we divide 2 by I, we get that, so we divide it by I, so we get A1 minus A2 equals 0. And therefore, we know that A1 equals A2. And we now substitute this into 1. So 1 is saying that A1 plus A2 equals 0, but we know that A1 equals A2, so this is 2A1 equals 0. And therefore, A1 equals 0. And since we know that A1 equals A2, A2 equals 0. So we have seen that the only solution to this system is that A1, A2, and A3 are all 0. That's the only solution that this system has. Therefore, the vectors are linearly independent. Okay, so that was part A. They are linearly independent vectors. Next, part B says, if they are linearly independent, they can be used as a basis. That's true. Now we can use these 3 vectors as a basis. And we know that the 3 vectors are linearly independent, so they are pointing in different directions. And therefore they span. What's the dimension of the span? If they are 3 vectors and they are linearly independent, the span is a 3-dimensional space. So between the 3 vectors, they span all of the 3-dimensional space. Okay? So this means that we can use them as a basis. So now the question asks, expand the following vector, u equals I2. So let me write it down here. So this is a vector. And we want to expand it into the basis v1, v2, v3. Okay? So how do we do it? Well, you know that expanding a vector into a basis is solving a system of equations. So this time we need to solve the following. So we need to solve the system a1 times v1 plus a2 times v2 plus a3 times v3 equals u. So we need to find which linear combination of the basis vectors, so with the coefficients a1, a2, and a3, gives rise to the vector u. That's what expanding a vector in a basis means. So we need to solve this system of equations. Which is the same thing as saying that we need to solve these three equations simultaneously. So now we proceed very similarly as we did in A. So first, from 3, we already know that A3 has to be equal to 2. Now from 2, if we divide equation 2, we divide both sides by I, then we arrive at A1 minus A2 equals 1. So therefore we know that A1 equals 1 plus A2. And now we substitute that into 1. So equation 1 says that A1 plus A2 equals I. But if we substitute this thing, then we get that 1 plus 2A2 equals I, which means that A2 equals I minus 1 divided by 2. And since we know A1 equals 1 plus A2, this is 1 plus I minus 1 divided by 2, which is 2 plus I minus 1 divided by 2, 1 plus I divided by 2. That's the value of A1. So that's it. We found the three coefficients, A1, A2, and A3. If you wanted to check this, you could get this expression, and then we write in as A1, A2, and A3. We can write the corresponding numbers. So A1 is 1 plus I divided by 2. A2 is equal to I minus 1 divided by 2. And A3 equals to 2. And you should be able to very easily check that when you add up the three vectors on the left, you end up with the vector on the right. Yeah. So this solved the system. So we expanded this vector in this basis. So what does this mean? This means that vector vector u, which is equal to I2 in the basis x, y, z, we could say that this vector is also equal to I plus 1 divided by 2, I minus 1 divided by 2, and 2 in the basis v1, v2, v3. Yeah, that's the meaning of expanding a vector in a basis. Okay. The next question asks, what is the projection of vector u equals I2 into the direction of v1? Okay, so we have this vector u, and then we have this vector v1. Even though I'm drawing them as if they were arrows, remember that these vectors are complex. So you cannot really imagine them as arrows in three-dimensional space because they are complex arrows. However, for picturing what the problem is asking, it's useful to draw them. So what we're being asked now is to find the projection of u into the direction of v1. So we are being asked to find this vector here. It's the projection of u in the direction of v1. Okay? Now, how did you find projections? If we scroll upwards, you remember we had a recipe for finding the projection of a vector into a subspace when the subspace is given by several vectors that are orthogonal. Now, we can say that projecting into one single vector is like projecting into a subspace which is made up as the span of one single vector. Yeah. So instead of projecting into a plane, we'll be projecting into a line. And therefore, we would be able to simply use the first term of this recipe because our subspace only has one vector E1. Okay, so that's the recipe we're going to follow. Therefore, the projection of U into V1, let's call it projection of U into V1 is, and we follow the recipe, and the recipe is U times vector V1 divided by inner product of V1 with itself multiplied by V1. That is the recipe for the projection of a vector onto another. This means we have to do inner products, yeah? So let's do this. So this is equal to the inner product of two vectors, which are I2, and vector V1, which is 1, I0, divided by the inner product of 1, I0 with itself, and this multiplied by V1, which is 1, I0. Okay, so let's do these inner products. How do we do inner products between vectors that are complex? So remember, we found the following way of doing it. So here we said that the inner product between two vectors, if they are written in an orthonormal basis, and right now we have the vectors written in the xyz basis, is simply given by the sum of the products of the coefficients, but conjugating the second one. Yeah. So that's the equation we're going to use for calculating the inner product. So basically we could write here in the side that A inner product with B is the same as doing the dot product of A times B conjugate. So we conjugate the second vector. Yeah. So let's do that. How can we write it? So I can think of several ways. We can either do it directly. So let's do it directly. So it's the first element multiplied by the second element complex conjugate. So I times 1 complex conjugate plus second element multiplied by the second element complex conjugate. So that's I times I conjugate plus the third element, which is 2 multiplied by 0 complex conjugate. So it's 2 times 0 complex conjugate. Divided by, now we do the inner product on the bottom here. So it's 1 times 1 complex conjugate plus I times I complex conjugate. Remember, the complex conjugate is acting only on the second one, yeah? Plus 0 complex conjugate. That's 0. And then that, we need to still multiply it by the vector 1, I, 0. Okay, so let's do that. So what's I times 1 complex conjugate? That's the same as y times 1. Let's do all the complex conjugates first, okay? So what's the complex conjugate of 1? It's 1, because it's a real number. And the complex conjugate means changing the sign of the imaginary part of the number. So the complex conjugate of 1 is 1. Plus I times the complex conjugate of I. What is the complex conjugate of I? It's minus I, right? Plus 2 times 0, that's 0. Divided by 1 times the complex conjugate of 1, which is 1. Plus I times the complex conjugate of I, and that is minus I, plus 0. And now we multiply this by 1, I, 0. So next we just do this addition. So this is I times 1, that's I. And then plus I times minus I, that's plus 1. So it's I plus 1, plus 0. Divided by, on the bottom we have 1 times 1, which is 1, plus I times minus I, which is 1. So 1 plus 1. multiplied by the vector here, which means we have I plus 1 divided by 2, 1, I, 0. And that is our final answer. So this is the projection of vector u into the direction of v1. Okay, so we simply used this recipe, and then for calculating the inner product, we used the fact that we just have to multiply each component by the corresponding component, but always doing the complex conjugate of the second vector only. Yes? Perfect. That was the answer for this part, for C. The next part asks, is v1, v2, v3, the set of three vectors, is it an orthogonal basis? And is it an orthonormal basis? So we need to check those things. So remember, what's the definition of orthogonal basis? Orthogonal basis, if and only if the inner product between vi and vj is equal to 0 if I is different to j. That is the definition. That's the definition of orthogonal basis. Yeah? So what does it mean in practice? Here we have v1, v2, and v3. We have three vectors. So we are saying that the inner product between any of these two has to be 0, as long as it's not the same one with the same one. So v1 times v2 inner product should be 0. v1 times v3 inner product should be 0. And v2 times v3 inner product should be 0. So these three inner products should be 0. Why those three? Those are all possible pairs that we can find. So we can do this one with this one, or we can do this one with that one, or we can do this one. No, sorry, we can do this one with that one. Those are the three possible pairs. Yeah. So that's what we need to check. We need to check if those three inner products are 0. So let's do that. So v1 times v2, that's the inner product of 1i0 times 1 minus i0. I'm just copying those from the question. Yeah. So how do we do the inner product? Remember, we do the dot product of the first vector times the complex conjugate of the second vector. So we do 1 times 1 complex conjugate plus I times minus I complex conjugate plus 0 times 0. And that is equal to 1 plus I times the complex conjugate of minus I. So what's the complex conjugate of minus I? It's equal to plus I. Yeah. And therefore this is equal to 1 plus minus 1, which is equal to 0. So the first equation is fulfilled. Now we need to check the second one. So the second one is v1 times v3. And this is equal to this inner product. 1i0 times 0, 0, 1. Now instead of doing it directly, I'm going to do another notation, just because it's nice that you see different ways of doing it. So I could say, apply the fact that inner product of A and B is equal to the dot product of A with the complex conjugate of B. Yeah. So I could say that this is equal to 1i0 dot product with the complex conjugate of this second vector. But since this second vector is 0, 0, 1, the complex conjugate is flipping the sign of the imaginary part. This vector has no imaginary part. So this is simply the dot product of this vector with this other vector. And the dot product is very easy. It's 1 times 0 plus I times 0 plus 0 times 1, 0. Okay, so this second case is also true. So let's check the third case, v2 times v3. So that's equal to 1 minus I0 times 0, 0, 1. And you can see that we have something times 0 plus something times 0 plus 0 times something. So it's also 0. It's very easy to calculate inner products. So the third equation is true. So the 3 are true, and therefore this basis V1, V2, V3 is an orthogonal basis. This is beautiful. So we have found a basis of 3 vectors, these ones here, that they are complex vectors, and yet they are an orthogonal basis in 3-dimensional space. Yeah. So any vector you want, you could write it using these 3 vectors. And actually, this is not a choice that I did arbitrarily, but this is a very common basis, for example, in electromagnetism, which is my field of research. So the electric field is very, very commonly, instead of expressing the electric field in the XYZ basis, when it's a propagating electric field, we like to express it in this basis, because these 2 first vectors are circularly polarized electric fields with opposite-handedness. So it's a very convenient basis. I don't want to go into the details, just wanted to point that out, that this basis, you might come across this basis in the future. It's an orthogonal basis. Okay, but the question doesn't end up there. The question also asks, is it an orthonormal basis? So let's remember what orthonormal means. So orthonormal basis if and only if the inner product between any 2 vectors is equal to 0 if I is different to j, and equal to 1 if I is equal to j. So the first condition we already checked, because that was the case for orthogonal basis. So now we need to check if the inner product of vi with vj is equal to 1 if I is equal to j. So what do we need to check? We need to check whether v1 with v1 is equal to 1, v2 with v2 is equal to 1, and v3 with v3 is equal to 1. So this would mean that the norm of these vectors, v1 squared, v2 squared, the length of v2 squared, and the length of v3 squared would be equal to 1. Yeah, so it would mean that the 3 vectors are unit vectors in terms of their norm. So the norm is 1 for all of the 3. It must be true for all of the 3. So let's start with the first pair. Let's start with the first case, v1 inner product with v1. So this is equal to the vector 1i 0 inner product with 1i 0 with itself. Now let's use the notation of the dot product. So this is equal to the dot product between the vector and the complex conjugate of the second vector. Okay? So what is the complex conjugate of the vector 1i 0? So the complex conjugate, as usual, is flipping the sign of the imaginary parts. So the complex conjugate of 1i 0 is 1 minus I 0. And now we need to do this dot product. So this will be 1 times 1 plus I times minus I, which is equal to 1 plus 1, which equals 2, which is not equal to 1. So this first test failed. This is not true. We do not need to keep checking. If one of these is not true, then the basis is not orthonormal. For the basis to be orthonormal, the 3 would have to be true. Yeah. So in this case, it's not orthonormal because the first one is not. If you wanted to check, you would see that the second one is also not true, but the third one is true. But still, that's not enough. The 3 of them has to be 1 in order for the basis to be orthonormal. Okay, so next. The next question asks, if v1, v2, and v3 are an orthogonal basis, which they are, this means that we can use a simplified method to expand any vector into this basis by using the inner product. Repeat part B using the simplified method. And here, for convenience, I copied part B. Part B asks us to expand the following vector u equals I2 into the basis v1, v2, v3. Let's remember what we got as our answer for part B, which I did solving a linear system of equations. So the answer was that vector u is equal to I plus 1 divided by 2 times v1 plus I minus 1 divided by 2 times v2 plus 2 times v3. That was the result that we got solving it using a linear system of equations. So now we are going to solve it using the recipe for the components of a vector in an orthogonal basis. Let's scroll up and look for that recipe. Here it is. So the components of a vector v in a basis e1, e2, and en. So each component vi is given by this equation here. The inner product of v with the vector of the basis divided by the inner product of the vector of the basis with itself. So let's apply that recipe to our case. So here we know that u will be equal to a1 times v1 plus a2 times v2 plus a3 times v3, because v1, v2, v3 form an orthogonal basis. And therefore, since they are an orthogonal basis, the coefficients are given by this recipe here. The inner product between u and v1 divided by the inner product between v1 with itself. So remember, I mean, this is very important. So we know our vector u, and we know our basis vectors, v1, v2, v3. So in order to calculate the coefficients in this basis, we need to put the vector that we want to expand, inner product with the vector of the basis, and then divide by the inner product of that basis with itself. Yeah? So why v1 and not v2? Well, because we are calculating the first coefficient, the coefficient of v1. That's why we only use v1 here. Okay, so let's do that. So that's the inner product between the vector u, which was I2, and the vector v1, which was 1, I0. And we have to divide that by the inner product of v1 with itself. So this is equal to, now instead of doing the notation of the dot product, I'm going to directly write the result. Yeah. So it's the first element times the complex conjugate of the second element. So that's I times 1 complex conjugate, which is 1, plus the second element, which is I, times the complex conjugate of the second element, which is I. So that's going to be I times the complex conjugate of I, which is minus I. This time I'm doing everything in a single step, because it's very easy to do in your head once you get used to it. And then plus 2 times 0, which is the third element, times the third element complex. And this we divide by the inner product of the vector with itself, which by the way we already did in the previous question, but just to reinforce, this is 1 times 1 complex conjugate, which is simply 1, plus I times I complex conjugate, which is minus I, plus 0 times 0. Yeah. So the result of this is I times 1 is I times minus I is 1, and then on the bottom we have 1 plus 1, so we have 2. So that's the first coefficient in this orthogonal basis. Notice that it agrees with what we got solving a linear system of equations. So far so good. Let's check the second one. A2 equals u inner product with v2 divided by v2 inner product with v2. So this is equal to I2 inner product 1 minus I0 divided by inner product of 1 minus I0 with itself. So once again, let me do it in a single step. So this is going to be I times the complex conjugate of 1 plus I times the complex conjugate of minus I, which is going to be I, plus 2 times 0 divided by 1 times complex conjugate of 1 plus minus I times the complex conjugate of minus I, which is I, plus 0 times 0. And this is equal to I minus 1 on the top and 1 plus 1 on the bottom. I minus 1 divided by 2. Correct. That also matches with the second component that we found using the linear system of equations. And finally, for A3, it's U inner product with V3 divided by inner product of V3 with itself. So this is equal to I2 inner product with 0, 0, 1 divided by the inner product of 0, 0, 1 with itself. So this is equal to I times 0 plus I times 0 plus 2 times 1 complex conjugate, which is 1. And the bottom we have 0 times 0 plus 0 times 0 plus 1 times 1 complex conjugate, which is 1. So we get 2 divided by 1, which is 2. Correct. And it matches with what we knew from part B. So with this, we end this very long problem. And you can see we have practiced a lot of things. So we started by checking if the vectors are linearly independent. So we had to solve this equation. Then we practiced writing a vector in a different basis, so expanding a vector in a certain basis, and for that we need to solve this system of equations. Then we talked about projection of a vector into a subspace, and that's what we did it. So we used this formula here. Then we talked about checking whether a basis is orthogonal and or whether it is orthonormal. Yeah, and you saw it was very easy. And finally, we repeated part B of expanding a vector into a basis, but using this simplified recipe when the basis, which only works if the basis is orthogonal. Okay, so since we proved that this basis is orthogonal, then this recipe works. And the beauty of this recipe is that every coordinate, every component A1 depends only on the vector V1. It doesn't depend on the others. That's thanks to the fact that they are an orthogonal basis. Yeah. Okay, so that solves the problem. Thank you very much for listening.